Désolé, il y a eu des contretemps.
Okay. Hello, everybody. My name is Sergey. I'm really happy to present this work to you. So this work, we will present it at Clear 2021. And this work is about how you can combine gradient boosting decision trees for graph data with graph neural networks. The outline of this talk will be, I first will give you a little bit of background to graph neural networks and GBDTs. Then I will talk about our architecture that we will present and show you a little bit of experiments. So in general, in machine learning, you can think that there are two types of models, two very popular and distinct ML models. One is neural networks, and another is gradient boosted decision trees. And they all have their pros and cons. So for neural networks, you can think that you have automated feature engineering, which means that you, for example, for images and text, you don't need to design specifically the input features. You can also transfer knowledge from one neural network to another. You can use pre-trained neural networks and then adopt this neural network for other tasks or applications. You can also do end-to-end training with neural network, which means that, for example, you can have a neural network that operates on images, you can have a neural network that operates on the text, and you can combine the outputs of the two models and train them end-to-end simultaneously. On the other hand, GBDT or gradient boosted decision trees, they have their own advantages. Namely, they pre-process the input features really well. So if in neural networks, you usually need to scale your data, you need to have all the features to be from 0 to 1 so that they have the same numerical type. In gradient boosted decision trees, you can have features of different types, of different scale, and that's why they have been popular for competitions in Kaggle, for example. They're also very efficient for heterogeneous data. So let's say if you have a feature corresponding to the age of the person or to the gender, they can process this really well because at every node in the tree, they process an individual feature. And finally, looking at the decision tree outcomes, you can get some interpretation of which input features matter in your data, and that could be important for business applications. So the question that we asked, is it possible to get the best of both worlds for graph learning tasks? And I'll first give you just a short introduction because we just had it for what graph neural networks are, and then I'll move on and speak a little bit more about GBDT. So graph neural networks, I consider them as a black box functions, which aggregates neighborhood features of every node and apply some nonlinear functions on top. So you put some graph with the node features, so you should have always some node features in every node. You put it through the black box called graph neural network, and you get the same graph, but now the node features are different. So they have been updated using the topology of the network. And the way they update it is through this message passing algorithm. That's one of the most common ones. There are some others, but typically what you have is you aggregate your neighborhood embeddings, and then you combine it with your own embedding. And this combined function also has some nonlinearity, like MLP, for example, or attention-based model. And the way you train GNN is through stochastic gradient descent or through gradient descent in general, which is the way we train all of the neural networks. So this is very common. I guess you all know about this. Usually in semi-supervised learning, you have a graph. You have node features for all of the nodes, but then you have only part of the training labels. So let's say for nodes E, J, and K, you have the target labels that you want to predict. And for other nodes, such as U and V, you don't have the target labels. So those can be considered as test nodes, and therefore you don't use them You don't use these labels during the training. And what you do, you pass this graph through the GNN. GNN gives you new updated node embeddings. After that, you make prediction for nodes E, J, and K with MLP. So you predict from 3-dimensional vector to the number of classes that you have. And then you have your favorite loss function. So for example, cross entropy. You compute the loss function and you update the parameters of MLP and GNN together. So using backpropagation. So this is very standard. There is no novelty. Now I'll talk about gradient boosted decision trees. So I also think that a lot of you know this, but I think it's important later to understand this concept, how exactly gradient boosted decision trees are trained. And they are trained in a different manner than neural networks. So what is gradient boosted decision trees? You don't have any graph. So first of all, you cannot apply GBDT to graph data straightforwardly. Like there is no way for GBDT to handle graph structure data as well as some text data or image data. So the only level of abstraction that they operate on is numerical vectors. Not necessarily numerical, but vectors. It's also called tabular data. And you have this observation, F1, F2, F3, F4, and you put it through a first decision tree, which is already built to you, let's say. And then you have a second decision tree. You also go through this decision tree. You look at the feature 4, and you check whether it's less or equal than 0.5. And if it's yes, you go to the left. And then eventually you end up in some leaf. And you do it for all of the trees that you have. And then in the end, you just take the sum of these outcomes for every tree. So you take 0.54 plus minus 0.3 and so on. And the way gradient boosted decision trees are built is through the minimization or through additive functions. What it means is that if you build already 2 trees, you keep them fixed, you freeze them, you never touch them, you never update them. And you add additionally a third tree, which would minimize the error that has been done by these 2 trees, plus this additional new tree. So this is a bit abstract, so let me give you a particular example of how we build a single decision tree. So this is an introduction. You may learn it in your textbooks. So you have this input data, which is the table of features. So every row is some observation and every column is some feature. And then you have a target label. So this is your training data. And then you need to build the root of the tree. So the first node of the tree. What you need to do is you need first to decide which splits can you have in your data. So the splits will be the feature name and also the values that the feature column can take. So for example, for F1, the possible values are 4 and 5, as you can see in the training data. So these are the 2 values, and therefore you have two possible splits, F1 4 and F1 5. And for the column 2, you have also 3 possible values. So this is 7, 8, and 9. And therefore you have F2 7, F2 8, and F2 9. And you have similarly for F3, 2 values, F3 2 and F3 3. So these are possible candidates that you can put as a split on the root of the tree. And then you need to decide which one will be picked. And the way it's chosen is that you look at how each split performs in separating your data. And more formally, you have normally your loss function. So in the regression task, it could be just a mean squared error. And you look at the part of the data. So for example, here you have an example, F1 less than equal than 4. So this is the first split that you can have. It would split the data in these 2 parts. So it would be T left and T right. And this, for every split, you can compute the average prediction, average target label that you have. and you can compute the loss for every of the parts of the data. So in this case, your average prediction would be 2/3 because you have 2 ones and 1 0. So in total, the sum will be 2, and you have 3 observations. So the average prediction will be 2/3. And then if you compute the H function, which is your loss function, that would be 2/9. You can compute it using this formula. And you can do the same for the right split, for the data that went to the right. So it will be 0. And then the total loss of this particular split here, will be the weighted sum of these two losses. So you have 2/9 multiplied by 3 observations that you have here, divided by 5 because you have in total 5 observations, plus 0 loss multiplied by 2/5. So in total, your loss will be 2/15. And therefore, you can say that the loss function, the loss value that you get for the split F1 and 4 is 2/15. Now you can do this the same for all other splits. So for the second split, for the third split, and so on. And you can get these loss values. And in the end, you pick the node, you pick the split that gives you the minimal loss. So you want to minimize the loss at every node. That's how you decide on which splits you assign to every node in the tree. And so in the end, your single decision tree, what it does is that you have this data, and through this procedure, you decided which split will be on the root. Then the data has been split, and with this data, now you decide which split do you pick for the next node, and so on until you reach some level of the tree. So, for example, you decide that you have the height of the tree will be equals to 2. So at this point, you can compute the average prediction for every leaf, and that's how you build your single decision tree. Now, how do you actually do GBDT training? So GBDT means gradient boosted decision tree. It's not a single. It's not a unique type of how you can build several trees together. So, for example, you may heard about random forest or extreme forest and so on. Even boosted decision trees, which is also another procedure. But the most popular one, which was popularized by Kaggle competitions, is called GBDT. And you have several implementations such as XGBoost or LightGBM that you may heard as well. So how GBDT training is performed. So you have the input data here, and you build a first tree as I just described to you. So you know already how to build the first tree. You get some predictions for every observation here. You get some prediction, and then you can compute the loss for every prediction. So T1x here means that for every observation you got some prediction using this decision tree, and you can compute the loss between the predictions of the tree and the real ground truth values. And then what you do is you take the gradient of this loss with respect to the predictions that you have from the tree. So this would be the minus dl divided by dt1. And the core concept of gradient boosted decision tree is that on the second decision tree, you now predict not the original target values, but you predict the minus gradient of the loss with the previous decision tree. And the idea, the intuition why we predict this value is that when we will combine the predictions of the first tree and the second tree, we want the second tree to minimize the error that was done with the first tree. And to do so, we will move in the directions of the negative gradient, because the negative gradient shows us how to decrease the loss functions in the best possible way. So now you use the same input data here. The tabular data here is the same as in the first tree. but your target labels has been changed to the minus gradient of the loss functions. And so right now I'm just speaking about the, it's common knowledge, it's nothing new. This is how GBT training works. So you build the second tree with this data. It will be different splits on every node. And then what you do is you sum the predictions of the first tree, so it will be T1x, and also with the second tree, T2x. You get the predictions, new predictions here. You compute the loss again with this new predictions TXI. And you compute the minus gradient again with respect to this new predictions TXI. And then you use this minus gradient again with the third tree of your model, of your GBDT. So this is the core training of GBDT, how GBDT are built. So every new tree approximates the error of the previous tree. The main message that you need to get here is that you don't want to update any parameters of your previously built tree. So for example, if you already decided that here you will have the split F1 and 4, you will never update it in the future. This is different from neural networks, because in neural networks, you have the parameters which are constantly updated by gradient descent. And here, instead, you have parameters that have been decided, and then they stay frozen until the rest of the training. And here's the another way to look at it. In the gradient descent in GNN or neural networks in general, you have gradient descent in the space of parameters. What it means is that you have a function that is parameterized by some theta parameters, and your gradient descent, it updates these parameters by moving in the direction of the negative gradient. So we know from the analysis, from the calculus, that this new loss function will be less than the old loss function if you pick the right learn rate. Now, the way I described GBDT, the training of GBDT, you can say that it's a gradient descent, but not in the space of parameters, but in the space of functions. So now you think that you have a space not of the numbers, but of the functions. And you pick some initial point in the space of function, which will be some function. And then you start moving from that function to another function. So every time you kind of add some additional function to your existing one. So this is written here. You have a function which will be the sum of functions. So you start with some first tree, and then every new tree, it will be the previously built trees minus a negative gradient of the loss function. And you can see that it will be also, the loss functions will be also decreasing if you pick the properly this learn rate eta. Okay, so this is background. Now, we want to combine gradient boosted decision trees because they're great. We know that they work really well on heterogeneous data, but we want to apply GBDT on graph structured data. And this is our architecture. This is what we suggested. As an input, we have a graph and the node features, and we will first take the node features from the graph without any graph topology. We'll put it through the GBDT component. So let's say we build the first tree or the first k trees with these node features. This GBDT will give us some prediction, and we will use this prediction from GBDT as new node features for the graph. So now we update the original node features with the prediction of GBDT. So GNN will take the original graph plus the node features, which will be the predictions from GBDT. And then GNN will make a typical prediction using the message passing algorithm with this data. And we can compute the negative gradient of this loss function with respect to updated node features here. So we can take the gradient of the node features as well when we make predictions. And we can get the minus gradient of the loss function here. And the new tree will be built using the original node features and this minus gradient of the loss function that came from the GNN. So here are a few properties of this model. First of all, you don't need to preprocess your data as you usually need for GNN, which means that if you have, for example, missing values in your data, or you have categorical features in your data, or if you have different scales of your data, let's say like you have income, which could be of thousands, and you have age, which could be of tens, you don't need to preprocess that explicitly because node features will be put through the GBDT component. It could be integrated with any GBDT model, XGBoost or CatBoost or like GBM or whatever, and GNN model. So it could be graph attention network, it could be Chebyshev network, whatever network you want to have, you can put it here. So it's model agnostic. It's end-to-end training, which means that you build the trees together with GNN. It's not that you first build all of the trees of your GBDT and then you train the GNN afterwards. It's actually you build one tree or the first 10 trees, then you update parameters of your GNN. Then you build the second tree, and then you update parameters of your GNN. And then you continue that for as many epochs as you want. And it has several interpretations. So one interpretation is that you can think about it as just a typical GNN, but it has additional embedding layer at the beginning. And this embedding layer is your GNN GBDT component. Or on the other hand, you can think about it as a GBDT, but your loss function, it's not mean squared error, but it's parametric function parameterized by GNN. So GNN becomes your loss function. You can think about GNN as a loss function. Okay, so now let's talk about inference. So assuming when you already build the model, how do you make an inference with your data? So in that case, you already have GBDT and you have a GNN. And in the next slide, I will explain how you actually build GBDT and GNN more explicitly. So in that case, what you do, let's say you have a production system, it gives you some graph, and then you first collect the node features, you put it through GBDT, it will give you some predictions, and then you append these predictions to the node features that you have here. And then you use this graph with the updated node features to GNN, and then GNN gives you the final predictions for every node. So this is when you already have GBT, you first collect the node features, update the node features with predictions of GBT, and then GNN makes final prediction for your data. Now, how do we actually train that? So it's built in epochs. Epoch means that we build one tree or k trees. Let's say we build one tree and we make one backpropagation for GNN. So how do we do this? Well, we have a graph with the node features for every node, and we have the training set of nodes, which means that for these nodes we have some target labels. So let's say for nodes E, J, and K, we have the node labels. For nodes U and V, we don't have them. And we put this training data to build one decision tree. So in the background, I already explained that if you have the training data, tabular data, you can build one decision tree. And then this decision tree can make predictions for all of the nodes, not just for the training nodes, but you can give the vector for node V, and it will give you the prediction for node V. And then you use this prediction to concatenate with the original node embeddings. And then you use this graph, which is here, and the training labels of the training nodes to update the GNN. So you give this data to GNN. GNN gives you new predictions for all of the nodes. You use the training nodes to compute the loss functions. And then this loss function will give you the minus gradient to update parameters of GNN with gradient descent. But it would also give you the minus gradient to build the second decision tree. So we will use this minus gradient of the loss functions with respect to the node features here, with respect to these ones, to build the second decision tree. So the second decision tree is the same procedure, but now the only thing that changed is this part, this target labels. So we don't use the target labels, the original ones, but we use the minus gradient that came from the previous epoch. And so we build the second decision tree, and now you see that there are two decision trees. You update the node features, you come here, you have the GNN, which was already updated with gradient descent before, you compute the loss function, and then you repeat the procedure. So you update the parameters of GNN, you get the minus gradient with respect to the node features, and you build a new tree. So as many epochs as you want, let's say 1,000 epochs. So eventually you'll have as many epochs that you want, and as many back propagation updates for the GNN functions. So this is the core of what we call boosted graph neural network, and this is what we propose to in this paper. Now let's look at the experiments, and we try to two comments. So first of all, we try to be as fair as possible, which means that we have been doing fair train test splits. So we had 5 random seeds. For every random split, we computed 3 times the same setup. We have hyperparameter optimization for all of the models, including the baseline models. That's the first comment. The second comment is we wanted to understand the kind of the pros and cons of our model. So the task that we experimented on is a node regression, semi-supervised node regression, and semi-supervised node classification. So here we asked ourselves 2 questions. Does a combination of GBDT and GNN, as we just described, gives you better results in terms of the classification accuracies and RMSE? And the second question is our boosted graph neural network architecture end-to-end better than if you first pre-train GBDT on the node features, and then you would use the predictions of the GBDT with GNN. So let me get back to the previous slide. So here we train it end-to-end, which means that every new tree uses the loss functions of GNN. But you could, for example, take the original node features and node labels, build all of the trees, and then add here the prediction of all of the trees, and then train separately GNN. So that would be a decoupled approach, which we call here residual GNN, res GNN. And we compared it to several types of models. So first of all, it's just pure GBDT models. So we tried with LightGBM and CatBoost. Then we have pure GNN models, which is graph attention network, graph convolutional network, and 2 other GNNs, which have been recently published in ICML. And then what if we take a fully convolutional neural network? So this is a deep neural network, which doesn't take into account the graph structure. And this is fully convolutional neural network, which is doesn't use graph structure, but it gives the predictions, and then these predictions are used together with the original features, and they're provided to GNN. So this will be similar to ResGNN. And the only difference between ResGNN and FCNN GNN is that FCNN GNN uses a neural network, and ResGNN uses a GBDT component inside. And you can see, so the gap means that it's the difference between the model and the GAT graph attention network here. So you can see that for 4 data sets, for node regression data sets, the top performance is achieved using the combination of GBDT and GNN. I need to say here is that a lot of the data set that people try in publications, they are homogeneous in the sense that the node features that you get, they already from 0 to 1, they usually come as pre-trained embeddings, for example, word embeddings. But in a lot of real applications, your node features, they are not scaled, not pre-processed. So for example, at Criteo, we have features corresponding to the time, like how many sales, how many clicks did people make. And you could also, features corresponds to, for example, the category of the client, like whether it's a retail or it's a travel client. So it's very different type of features. And therefore, we use this 4 heterogeneous data sets, which have heterogeneous node features. They have features that really distinct between each other. They have different meaning. And this is homogeneous data set. It has back of words features, which means that they are very homogeneous. There is a lot of zeros and just a couple of ones. And you can see that in heterogeneous data sets, as we expect, the top performance is achieved by GBDT plus GNN architectures. While in homogeneous, it's usually that your typical graph neural networks perform really well. So you don't need actually to use GBDT plus GNN. So this is good insight. The second question that we asked is whether the performance gain is agnostic to the GNN model that we take, what GNN architecture that we take. So we tried BGNN, boosted graph neural network, with 4 different types of GNN models. So graph attention network, GCN, AGNN, and APPNP. And here you can see that with the red, you have BGNN, and with the yellow, you have ResGNN. So you can see that in all cases, you get much better performance, so the smaller the better, with the BGNN. So usually BGNN beats ResGNN, and in all cases, ResGNN and BGNN is better than the original GNN model that you use. So for example, here you can see that BGNN with the GAT, with the graph attention network, achieves 4% improvement, relative improvement over graph attention network, pure vanilla graph attention network, and ResGNN achieves 2% improvement. So it's really good to see that you can plug any GNN model here, and in heterogeneous data sets, you get improvement. So it's not specific to some specific GNN model. Another question that we ask is whether the running time is an issue for our Boost GNN, because you can think that you have now 2 components. One is GBDT and another is GNN. And you can think that your running time would explode, it would train for a longer time. But in reality, what happens is that your loss converges much faster with BGNN than with typical GNN. So GNN can take thousands of epochs, thousands of back propagations to be trained, while for BGNN, this is the green line here, it usually takes a few epochs. So usually within 10 epochs, you already converge to the minimum value. And therefore, the running time, so it's in seconds here. You can see that, for example, for BGNN, it takes 20 seconds, while for graph attention network, it takes 35 seconds. So even though a graph attention network has less parameters, has fewer parameters, it requires it to run longer, to converge longer. Therefore, the running time for GNN is usually the same or bigger than for BGNN. So it's also really good to see that BGNN is not really long to train if you set a step early stopping for your model, like if you track the validation loss and you see that your loss doesn't improve for some number of epochs, then you stop. Yeah, and we have additional experiments in the paper, but I will not go through them. So I think it's good. And if you have any questions, please let me know.